of all, why do we use linear programming? We use linear programming to basically maximize or minimize a linear function. That is the basic aim of linear programming. But this maximization and minimization is subject to some constraints. So constraints are those inequality, or maybe in some cases equality, which basically restricts the maximization and minimization of that linear function. Now, what is a linear function? I covered that specific thing in the algebra or introduction to basic mathematics. Now, this linear programming is used in various facets of the business decision making. For instance, if an entity wants to increase their profit or increase their productivity, or for that matter, increase their quality, they can use the linear programming subject to some constraint to either increase their profitability, productivity, and so on and so forth. The similar concept is of minimization. So in business context, if you want to take a decision regarding minimization of maybe wastage, maybe cost, maybe time, then one can use linear programming for that. Now, basically, there are two main components of a linear programming model. Now, what's a linear programming model? We apply linear programming or a linear programming model. And basically, linear programming model constitutes of two components. One is called the objective function, and the others are actually what we call the constraints. Now, objective function is that linear function which we want to either maximize or minimize. So if that objective function is represented by z, z corresponds to the maximization of that linear function. But if I place a z and place a small static over it, it becomes a minimization function. So for instance, if I write something like this, a maximization function, that is z equals to 300x1 plus 400x2, and suppose 500x3. This is a very basic, what we call a maximization objective function, in which the 300, 400, and 500 we algebraically call them as an objective function, right? This whole is an objective function, but the 300, 400, and 500, what we call it coefficients. But these are a special type of coefficient. We call them objective coefficients, right? Objective coefficients. Now, what are those? What is the nature of objective coefficient in a while? Now, moving on towards these x1, x2, x3. These are basically proxies for some products. So, for instance, if an entity produces three products, product A, product B, product C, so in order to make an algebraic equation out of it or an expression out of it, we just represent it with x1, x2, x3. So basically, the x1, x2, x3 are what we call decision variables, right? We call them decision variables. Now, so the variables in the objective function are what we call decision variables, while the objective function, we call them the coefficient in the objective function, we call them objective coefficient. Now, if the linear function, maximization linear function, is basically constructed to increase profit, right? So the 300, 400, and 500, we'll call them per unit profit of x1, per unit profit of x2, and per unit profit of x3. So this 300, 400, and 500, we call them per unit profit. So if it's a profit maximization linear function, if we call it, for instance, productivity maximization, or if we call it, for that matter, in a minimization context, if we call it cost minimization, then these coefficient will become per unit cost, right? So if I place something like this, z steric, and I just write it as a minimization cost function, then this will become actually a 300 cost per unit of x1, 400 cost per unit of x2, and so on and so forth, right? So this is basically an objective function. So objective function primarily consists of two components. One we call decision variable, and another one we call objective coefficient. Now, these are known. The objective coefficients are actually known in a linear maximization or a minimization function. What we want to determine is basically the values of these variable, decision variable. That's the name, decision. We need to take decision, how much to produce or how much to increase or decrease, right? About these red highlighted variables. We need to take decision. So basically, the linear programming try to find out the values of these decision variables. Now, moving on towards the constraint. What are basically constraints? So constraints basically limits the value of z and z static, that is minimization objective function and maximization objective function. And the constraint as particularly two components, we can call it the left hand side and the right hand side. So I'll write a constraint. So in a production process, if I'm considering some labor hours, that is amount of time spent in manufacturing a single unit, what we call that a labor hour, the breakup of it. So if an entity produce two products, A and B, and I proxy it with the x1 and x2, so let me write a very simple constraint inequality. So it's something like this. So I'll write x1 plus x2, and since this is a labor hour, so I just write 2 hours per x1 and 2.5 hour per product of x2 should be smaller than or equal to, suppose, 50 hours. Now these 50 hours, these are the total hours available. And what this 2 and 2.5 is, technically we call them parameters, right? These are what we call the parameters. In the former function right here, we call them objective coefficient. But right now in constraint equation, we'll call these as parameters. Now what are those parameters? So parameters are simply resource consumed per unit, right? Per unit of a decision variable. So 2 hours, it takes 2 hours to produce one x1. It takes 2.5 hours to produce one x2. And the total hours available for us, the sanctioned hour, these are 50 hours. So this one is the right-hand side, and this as a whole we call left-hand side. Now always remember, left-hand side represent the resource which is consumed, right? We tend to consume resource on the left-hand side of this equation, right? As per the per unit resource consumption values. While on the right-hand side, what we call it a valuable resource, right? So there is a huge difference. This amount is sanctioned, and we tend to use these amount with time in our production duration. So this is one of the constraint, and we call this constraint specifically less than or equal to, or we call it a upper limit constraint. Upper limit constraint. What is a upper limit constraint? Upper limit constraint is a sort of a constraint in which we cannot exceed some available resource value. So for instance, you have per week 50 hours of labor available in which you will produce some products. That is one of its example. And one could be, for instance, per week you have 150 square feet of storage available. So you can only produce products which can be easily accommodated in these 150 square feet, right? So always remember, whenever you see less than or equal to constraint, then the value at the left-hand side should be either equal to or less than the right-hand side value. You cannot exceed the right-hand side value. That's a restriction. That's why we call it constraints. Another constraints could be it could be the reverse of it. So in greater than or equal to, what we do is we reverse the equation, this inequality, and it's something like this. So for instance, and basically the second type of resource is used in very specific circumstances. For instance, you have a compulsion to produce some product more than some quantity. So for instance, if I say product C and I represent it with X3, so X3 should be equal to or greater than some units. So let's suppose 50 units. In some sort of a production process where you have a compulsion to produce some product more than some value, then we go and use this constraint right here, which is basically called the greater than or equal to. The last constraint is equality. Equality simply refers that the amount consumed at left-hand side should be exactly equal to the amount sanctioned at right-hand side. So these are the three types of constraints, and these constraints basically limits the value of Z static and Z. Then moving towards some rules of linear programming, before solving a linear programming model, we need to keep in mind these four imperative concepts. The first of all is linearity. So if I write some linear function, maximization objective function like this, 3x1 plus 4x2 plus 5x3, right? And another side, I write something like this, 3x1 square plus 4x2 plus 5x3. Always remember, a linear function should have an exponent of 1 corresponding to their variable. So here the exponent is 1, here the exponent is 1, here the exponent is 1, perfectly linear. But this one, the exponent of x1 is basically 2. It's not linear. So linear programming is only applied on equation which are represented as these. And the similar concept extends to the constraints as well. So all the decision variable in constraints should always be to the exponent of 1. If it's more than 1 or less than 1 for that matter, it becomes non-linear. So the first rule simply refers that the decision variable, which are actually these x1, x2, x3, which are actually the proxies of real product, should be linear in objective function and in constraint. The second compulsion or the second requirement rule of the linear programming is that the decision variable can accommodate the value of decimals. So there are two types of variables, the discrete and the continuous. Discrete, you just count, so 1, 2, 3, 4, 5, 6. So suppose number of students in a classroom, number of fans, number of chair, all of these you can count. There can't be 30.5 students in a class. That will always be a whole number, right? But on the other side, what are continuous variables? The weight of the students, each student, it can be a continuous variable. It can be represented in a decimal form. So the student can be a 70 kilogram, or the student can have the weight of 70.5 kilogram. So decision variable can accommodate the value of decimal, or we can write it in P by Q form. The next one is what we call the certainty. What's a certainty? As the continuous variable corresponds to what we call the decision variable, certainty corresponds to the parameter. So all these value in a constraints, which we discussed right here as an example, labor hour. So this 2, 2.5, and all these values, these are known in advance. If you don't know the values of parameters, you cannot solve the linear programming problem. The last but not the least, the very important, the most imperative one is the non-negativity constraint. What's a non-negativity constraint? A non-negativity constraint limits the value of decision variable, or in other words, the value of x1, x2, x3, and so on and so forth, in a only positive or zero value. So the decision variable can never have a negative value. They can never have a negative value. So for instance, if I have 3 decision variables, x1, x2, x3, then their value should always be greater than or equal to 0. So few things. The decision variable can accommodate a value in decimal. Decision variable can accommodate a value in a whole number. Decision variable can accommodate value in 0, but not in negative. The negative value is forbidden in linear programming, right? And it has a methodological implication as we go along.